Today, I will start this meetup explaining how to enable early data discovery for new products. And I will use financial markets examples that we had in the past. First, it's important to start explaining what product discovery is for us. At WBAA, mainly we create new products to deliver value to the bank businesses. By value, we mean three main components. It means the product should be desirable. That is that basically people want to use it. Second is feasible, which means we are able to implement it in a proper manner. Finally, is viable. This means, in general, it's profitable for the bank businesses. For this, we have multidisciplinary teams composed of UI researchers that, along with domain experts, do user research. This means they interview users to get insights from them. Second, we have data engineers that are ingesting data. In this case that we're going to explain, is going to be a real-time example because we have financial markets, so multiple sources in real time. We make this data available for the rest of the team. And finally, data scientists and data engineers, they work together to deploy modules and deliver PoCs that are validated in different iterations with the customers. Something important to remark here is that we ingest data even when the final product is not totally defined. We have to take this into account later on. From the data engineering perspective, this brings a basic example, really common design problem, which is basically we will design a scalable event streaming system. If we have to treat this as a recipe, the component would be first, we need different components to collect data from the sources and transport it in parallel. Second, this is a bank, remember, but this applies for every business in the world. We need a firewall to filter undesired data. Therefore, after this, we need a load balancer to balance the input work of the data. Basically, it depends on the volume. We will have multiple workers in parallel. This could be done in a round-robin way, but depending on the use case, you could define a different way of load balancer your problem. And after this, you get the data and you have to start storing this at some place. Basically, in most of the cases, you use a persistent log where you're going to write your data partition by one of the fields. In our use case, we will use the ingestion time. It means we will have a partition per year, month, and day. But again, depending on the use case, you could use your custom partitioner. This persistent log is not meant to store your historical data, only your streaming data. So you will need another place to store your historical data. This is going to be a different component. And finally, you need a process to orchestrate data movements or ETLs between the streaming component and the historical data component. With all of this together, we will have a scalable event streaming system. For the first two components, what we have is basically a GitLab pipeline. And with this GitLab pipeline, we are deploying different artifacts to Kubernetes, where we have our load balancer. And depending on the volume, we are deploying different pods. We can handle the first part of these components. Second, we have to choose the right persistent log. Remember, for this use case, we have a high volume of data. So we will need a distributed PubSub, which means we will have multiple publishers and subscribers reading and writing to the same data. It means we will have multi-tenancy for multiple applications. Besides, we will need to handle duplicates. We have multiple sources from financial markets. They could write the same message twice, and we will have to avoid these kind of things by applying components like log compaction. Then we have to handle also exactly one mechanisms. And finally, this log should be resilient. We know there are multiple options in the market. with different performance. There are multiple benchmarks. On the internet, but we had one in place already called Kafka, the famous Kafka. And Kafka complies with most of the requirements that we have here. Basically, it's resilient, we can handle duplicates, and we can handle a high volume of data. Has a PubSub, distributed PubSub. Once we have Kafka in place, we need to find a way to transport data from and to Kafka. So again, we have multiple options here. You have Flume, you have Flink, you have Spark. With all of them, you can move data from the sources to Kafka. But within the Kafka ecosystem itself, you have Kafka Connect. With Kafka Connect, you basically could deploy a cluster with different workers depending on the volume of the data that you're reading. You can move all this data to Kafka from the sources and then have different workers as well, moving data to different sinks, as you can see here in this diagram. The most important part here is that with Kafka Connect, you don't need to write a single line of code. Everything you need is a configuration file like this. Within this configuration file, there are different components that we always need to consider. The first part is that we will need to define different templates depending on the volume of the data that you're reading. In our case, we decided to use 3 different templates, one for high volume data, one for middle level of data, and some of them for small jobs. You can use regex for this. Basically, you name the topic in Kafka, depending on the volume, and you put at the end, for example, in this case, high volume row. This is important as well because with this, you define the number of tasks that you are running in parallel and the number of workers that you will have for this job. Also, very important here is that you need to define for how long you are going to keep the data in the buffer. You could use here 2 different strategies, buffer size, which means memory, or a linear time. And the most important part here is that you should avoid writing very small files, as most of us know you will cause many problems in the distributed system or Hadoop in the future if you do so. But you also have to avoid writing very large partitions, because this will cause out-of-memory issues as well. So you will need to find a balance between those 2 things. You need to define the partition key. For our use case, we decided to use the year, month, and date, but again, depending on the case, you will need to decide your custom partitioner in order to avoid skewness of the data. And it depends also always on the use case. Something that you could do with Kafka Connect is that you can write the error messages to a different topic. So you can define the name of the topic where you're going to write your messages in order to monitor them in the future. And for us, and our suggestion here is always define a common structure for the raw message. Our structure was basically we were adding always the raw data as it comes in a field called raw data. We were always sending the metadata, and we were sending as well the ingestion time in order to create the further partitioner. Once we have the data into Kafka, we need to decide where we're going to store all this data to make it historical, right? You always have 2 options. This is a never-ending discussion in the market. You have object storage versus block storage. In our case, we were more worried about elasticity than consistency for data that basically is continually growing, so we went for object storage. But again, this depends on the use case. We're going to write all this data serialized as Parquet to improve the performance, despite of all the schema evolution constraints that you could have, and you could solve with a format like Avro. But now we are preferring performance over schema evolution. So as you can see here in this diagram, we have multiple sources. For example, FTP, Cassandra, WebSockets, so on and so forth. We are reading from all those sources using the same message format. writing this to Kafka, and reading from Kafka and writing data to our final raw data lake. We have our own platform for this, which is called DAP, but this is not the topic of this conference, but basically we are storing everything in S3. Our own component, but in general, it's an object storage. One of the decisions that we have to make here is that we didn't have a business case defined in that moment. We had to define the final tables structure in order to expose them for the data scientists, right? What to do in this case? But we decided that we didn't have to pick a structure, to pick a schema, but we could infer that. For that reason, we decided to use Spark datasets at this stage. With the Spark datasets, we will store the final tables. First, we have a Spark job. Reading from the raw data, serializing this as Spark-it using snapping for the compression, and partitioning this data by year, month, and day to S3. And second, we are reading from the raw data field. We are inferring the data that we have there. We are flattening the table that we find, and we are storing a final table. Again, serialize as Spark-it using the ingestion time. You can see this process here. We are reading from the raw data, serializing the data, and inferring the inner data frame schema, writing all those data frames to the final serialized bucket. And we are exposing 2 external Hive tables from that location to make them available for the rest of the team. Something to consider here is that we want to overwrite only the data for the final partition. It means from the current date. So we use this option from Spark, which is called partition overwrite mode dynamic. And in this way, we are overwriting the data only for that specific date instead of the historical data. After all of this is in place, we have to monitor this process. It means we have to monitor that everything is working well. So we are using the GMS exporter from Kafka. We are sending metrics to Prometheus, and we are exposing a final dashboard using Grafana. Within Grafana, we could find different metrics. For example, the volume of data that we are reading all the time, the status of all the workers that we have in Kafka Connect, and we could see if we have any errors in every moment, checking that the data quality and the data counts are well defined for the pipeline that we are running. Then with all of this in place, we are ready to start creating PoCs together as a team. We have the data available. We can explore and create experiments that we validate with the customers every time. We are ready in case we need to ingest new data on top of this architecture to pivot if it's needed. And the most important part, we are ready to make all the decisions based on data. Once we decide that we're going to apply a business case, we can use this architecture and we can, for example, join tables. We could define a schema, so on and so forth. But this is going to be done only where we are ready for it. With this, I finished. Basically, the main idea here is that you can enable data discovery and product discovery by creating a very simple streaming ingestion process using Kafka Connect and Spark. You can expose final tables for the data scientists and start working on great products. That's it. Let me know if you have any questions.
There's a couple of questions on the chat.
Can you see them, Ronald?
I think you're on mute.
Oh, sorry, Rob.
So
No,
the question I see here is, what kind of performance drop have you noticed with using the schema registry? Actually, here we're not using the schema registry yet, as I told you before, because we didn't have a business case defined. So we decided to import the schema, right? But the schema registry will be in place only when you define the product that you're going to use. When you have a business case in place, you define the schema registry and you start defining the schemas. Of course, this will cause an overhead. In the past, for example, I used the schema registry to have a schema for Kafka, but our idea here is that we will always use Spark data sets to infer the schema. Any other question?
Maybe just summarize with exactly what your app is kind of delivering to users. So if you achieve everything you've described technically here, what kind of benefits do people see?
Basically, the benefits that you can explore data and you can start iterating with the customers, always based on data, the actual data that you're going to use for your product. In this case, financial markets is the use case. So you are streaming data from multiple sources. You deliver final tables. You can explore the data. You can create PoCs all the time. You can validate the PoCs with real data, which means you are enabling product discovery and data discovery from the beginning instead of actually use mock data for this validation.
Cool.
Ronald, there was another question.
One question for me. Why do you use a Spark Bash application in place of a Spark streaming? Because you're writing in your S3 bucket in real time. So you could just use a Spark streaming application to write back into your Hive database.
Yeah, that's true. Actually, we are storing the final raw data, just for experimentation. So we have the real-time data, right? We have the partitions. We have some final tables just to explore. But once we define the final use case, we will have to move all this data in real time as well and explore the data in real time.
One thing that might be interesting to you actually is this sprint we're experimenting with Delta Lake, which is the Databricks format of taking streaming data and making tables on the fly and then compacting them back in future into tables, but it kind of turns streaming data into native tables. The data liberation and area asset squads are looking after that, so it could be fun.
Yes, indeed. That's a good approach to follow there with Delta Lake. Actually, it's even better than what we are applying here, but with Kafka Connect, the advantage you have is that you always have the data in Kafka. You don't have to write a single line of code. You write the configuration file and you can expose final tables.
Cool. There's also a question on the chat from Xiao.
Yes.
What kind of metric?
Can you hear me?
Yes.
Yes. What kind of metrics? Because I see that you are using Grafana to do the monitoring. So what kind of metrics you can monitor in Grafana? Because I can't see the screenshot very clearly. That's why I'm asking.
We have different kind of metrics. We have the throughput first. How many messages we are reading per unit of time. We have also the number of errors. Sorry?
And you build this Grafana dashboard by yourself, or you use kind of predefined dashboard and then you just connect to your servers?
You could use some templates there, but actually in this case, we created the Grafana dashboard from scratch.
Okay, thank you.
So yes, in general, we have the throughput, we have the number of messages that are failing. Different components like the number of workers, number of tasks running per worker, so on and so forth.
Okay, thank you.
Feel free to get in touch with the team if you want some info on Grafana. We use it quite extensively. So DAP itself registers 800,000 metrics every second in Grafana, so we rely on it quite heavily.
And you are using the ING Grafana, or you have your own Grafana dashboard or server?
We do host our own because it needs to be, with the amount of traffic we put into it, it needs to be sitting right next to the platform.
All right, I see. Thank you.
Does anybody have more questions?
I can have one. How do you handle the failed reads? Because you mentioned that Kafka Connect can route the failed messages to some separate topic. So did you encounter such scenario, and what's your strategy for handling those?
Basically, you can define different strategies. One of them is lock them to a different topic. You can even ignore them in case you want. But our decision was to start logging them to a different topic and use Grafana to monitor those. Basically, we were showing all those errors with Grafana, and when you need to reader, just create a different reader to that topic and start checking why those messages were incorrect or had different errors.
Okay, thanks.
And to do that, basically, you have to go to the Kafka Connect configuration and just add the name of the topic that you want to use to log the errors. It's as easy as that.